Hello, this video is one of the modules on offer as part of the Foundation online training course. Our unique course has helped over 10,000 people to study for their foundation exam, and the course consists of online lessons, videos like this one, quizzes and mock tests. To access our free course and to get the latest version of this video and our collection of videos, go to www.hamtrain.co.uk. Now, on with the module.
Hi, this is Kelly from Essex Ham and welcome to Foundation Online, getting you started with amateur radio. Here's what we'll be looking at in this module.
Hello, my name's Pete and I'll be your guide for this module.
Transmitters and receivers. This covers the basic principles on how radio signals are transmitted and received.
In this module, we'll look at the various modulation types and waveforms. We'll look at sidebands, the block diagrams for transmitters and receivers, a little bit about software-defined radios, and how to set up your amateur radio station. We're going to start off with RF signals. A radio transmitter is used to send information from one place to another using electromagnetic radiation. A transmitter creates something called an RF or radio frequency carrier wave. This will be at the frequency that you'd need to tune your radio into, and it mixes the information to be transmitted. So you take the carrier wave and the signal that you want to transmit, mix the two together, and that is called modulation. On the screen here you can see a visual representation of a carrier wave. There are two types of signal that we need to be concerned with at Foundation: AM, amplitude modulation, and FM, frequency modulation. And we'll look at those in a bit more detail now. First off, let's take amplitude modulation, AM. So let's assume this is our audio signal. This could be some speech. And this is our carrier at the frequency that we want to transmit the signal. If you mix the two together, you'll be modulating the signals and you'll end up with an AM waveform that looks like this. And what you'll notice is the height of the waveform here and the dip, the highs and lows, match the highs and lows of our audio signal. So when the two are matched together, you should notice that the highs and the lows, or the amplitude, change according to the amplitude of the signal. That's AM. If we look at frequency modulation, you'll see the same principle but slightly different. So again, here is our signal. This could be some speech. The carrier is the same for AM and FM. And what's happened here is as the signal reaches its height, you will see the frequency between the waves, so the number of waves you get per second, will tighten. So the top here, top of the audio signal, a bit of tight space. Towards the bottom of the signal, you'll notice the gap is wider. So this is modulated by the frequency of the waveforms, the number of waveforms you get per second. Modulated together, your signal and the carrier give you signals modulated by the frequency. The height, you'll notice, is the same. So if we look at all of these together, here we can see our audio signal at the top and what an AM signal would look like, with the heights varying and the frequency varying here on the FM signal. Some others that you'll come across: CW, which is the abbreviation that's used for Morse code. We'll talk a little bit more about that in a future module, but CW is Morse. And you can see it's either on or it's off. So that'll be on, off. Once that's modulated, you'd see it's on or it's off. So signal, no signal, signal, no signal, etc. So Morse code, the tones are generated on and off by a Morse key. And for data, it's usually using a computer. Usually multiple simultaneous tones generated by an audio interface from a computer. So a computer could send out some audio via some software into the radio and transmit it as data. I'll give you a quick burst of a data signal. This one's called FT8, just so you know how they sound. Now we move on to something called sidebands. So if we were to look at an AM signal, this is where our carrier is. When the signal is generated, you end up with a signal below the carrier, which is called the lower sideband, and a signal above the carrier, the upper sideband. So this is the width, the bandwidth of your signal. When you're sending out a signal, the information in the upper and lower sidebands are the same. This actually means you can economise and just send one. You don't need to send them both. So in a mode called SSB, single sideband, you can get away with just sending either the upper or the lower. Instead of transmitting them both, you can use all your transmitter power in just sending one and not the other. So it's a very efficient way of sending your signal. If you're using sideband on a radio, for single sideband you use the lower sideband if you're transmitting below 10 megahertz. It's not always the case, but for the sake of what we're discussing today it is. So lower sideband operation is normally below 10 megahertz and upper sideband above that. Here's a screen from an HF radio. You can see we're using upper sideband on a frequency of 14 megahertz. Just something you'll need to remember: lower sideband below 10 meg, upper sideband above 10 meg, normally. Just before we move on to a new topic, we thought you might like to see how AM, SSB and FM actually look when received. Here I'm using a cheap SDR dongle, priced under £15, to see what received radio signals actually look like. Starting off with AM. Now, first of all, I'm going to turn on the transmitter with no audio. What you should see is the carrier on the centre of the screen. Here we go. Now, if I start to modulate the carrier by talking, you can see my voice appearing to the left and the right of the carrier. And I'm going to talk very quietly. Quietly, and I'll make my voice a little bit louder. You should be able to see that the waveform gets a little bit louder. Loud. Quiet. So that's what amplitude modulation looks like on a software-defined radio. What I'm going to do now is turn to the lower sideband. If I transmit on the lower sideband, this is what it should look like. 1, 2, 3, 4, 5, this is a test. You'll note there's no carrier here. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and the signal is on the lower side of the carrier. And let's turn to upper sideband. 1, 2, 3, 4, 5, this is upper sideband. If I talk very quietly, and now if I talk very loud, 1, 2, 3, 4, 5. So that is AM, lower sideband and upper sideband. Let's take a look at frequency modulation next. What I'm going to do now is give you a carrier with no audio. And now if I start to modulate the carrier, 1, 2, 3, 4, 5, test. 1, 2, 3, 4, 5, test. If I talk quietly, and if I raise my voice, 1, 2, 3, 4, 5. So that is frequency modulation, and here again is the carrier. Now, time to move on to transmitters. So let's run through some of the basics. A transmitter has 4 basic stages. The first one is the audio stage. This will get and amplify a weak signal from a connected microphone. Next is the frequency generator. This generates the carrier wave that we talked about earlier on the frequency that you'd like to transmit. As we mentioned, you have to mix these two together, the signal and the carrier. And that's done using something called a modulator. This mixes the radio and audio signals together. Once you've actually got your radio signal, it's then amplified using an RF power amplifier. This increases the signal and will feed it to the antenna. So we can look at this in a box diagram. Here's our microphone. So the microphone amplifier, or the audio stage, will take the weak signal from the microphone and amplify it to something that we can use. That signal goes to the modulator. There it's mixed with the radio frequency, which is generated by the oscillator, also known as the frequency generator. So this will generate the frequency that we'd like to transmit on, and the modulator mixes our audio frequency and our radio frequency. This will give us our radio signal ready to be transmitted. It's amplified in box 4, that's our RF power amplifier, and then sent off to the antenna. For the exam, it's very common that they'll say something like, what is box 2? And you'll be given a multiple choice option list like you'll see below. You're expected to know that this one in the middle here is the modulator. Don't remember the numbers because they can switch the numbers around. You'll need to know this is your amplifier, your audio amplifier stage, the stage that generates the carrier, the modulator that mixes the two together, and the RF power amplifier. If we look at an AM transmitter, here you can see our voice signal is coming to the microphone. It's being amplified to something usable. There's our carrier, the two modulated together, and then amplified to be sent off to the antenna. A little bit more on transmitter operation here. If the oscillator is not set correctly, you may find that you're transmitting on a frequency that you don't want to be transmitting on, potentially outside of the amateur band and likely causing interference. So the oscillator has to be set to the correct frequency. And the RF power amplifier stage must be correctly matched to an antenna. It's got to go to the right kind of antenna, which we did discuss in a later module. If you end up sending a lot of power into something that doesn't work as an antenna, you could risk damaging your transmitter. As it says here, there's more on matching the amplifier to the antenna in a later module. It's also important to get the transmitter audio levels to be correct. Excessive AM amplitude modulation can cause audio distortion. So remember our curvy waveform at the top there. If it gets too loud, you'll find the top and bottom get cut off, which can cause distortion as well as interference to other channels. Excessive frequency deviation can cause interference with other channels. You've got to set the mic gain correctly. Here you can see a picture of a radio with a mic gain. So you set that so that your microphone doesn't distort and isn't too quiet. And if you're connecting a computer through all of this, you need to check that the audio levels from your computer aren't too loud. Again, it can cause distortion or interference with other channels. Now let's take a look at receivers. A radio receiver recovers information that's sent from one place to another using electromagnetic radiation. The process of recovering the audio from a modulated radio signal is called demodulation. So you've got an antenna sticking up in the air, receiving signals on all different frequencies. You'll need to receive the signal, decode it, which is called demodulation. So the basics of a receiver, there are 3 stages. There's the tuning and RF amplification stage. This is where you tune into the frequency that you'd like to receive, and the weak radio signal will be amplified so that it can be used. Then there's the demodulator, sometimes referred to as a detector. This extracts the audio from the radio signal, called demodulation. There are different types of detector for each modulation type, for example, AM and FM. Then there's the audio amplifier. We've got rid of our carrier, we've now just got the audio left, but it's too weak, so we need to amplify it so it can be heard through loudspeakers or headphones. And here is the block diagram for the receiver. Here you have the antenna. Signals are received here. You tune to the signal that you're looking for and amplify it to something usable in the first box here, number 1. The amplified signal goes into the demodulator, where the carrier is extracted and thrown away, just leaving us with the AF, the audio frequency. It then gets amplified and comes out of our loudspeaker. Again, in the exam, you'll possibly see a diagram like this and be asked to identify or explain the functionality of these 3 boxes. Here's a more visual representation. Again, the signal comes from the antenna. It's received here. Here the carrier is removed and we have the remaining audio frequency left, which is then amplified to the speaker. A quick look now at software-defined radios. These are a new type of radio that are out there that, rather than using hardware and electronic components, use software to let you tune in to radio signals and transmit. As I say, they're relatively new. SDR, software-defined radio, they're increasingly more common, and they range from very cheap low-budget receivers that plug into a computer to large, expensive desktop transceivers. On the left here you can see a very basic dongle. They start from around £10 and they let you receive radio frequencies from all over the spectrum. Very good things to get started listening to radio with. And on the right here you can see a more expensive software-defined transceiver, which is a transmitter and receiver in one box. So how does it work? The software-defined radio gets its electromagnetic radio signals from the antenna and then digitizes the signals for processing in software and not hardware. We can look at this on a box diagram here. The incoming signals are converted from analog into digital, fed to a digital processor, and then converted from digital back to analog so that we can hear it. A mathematical operation in the software-defined radio enables all of the signals to be sifted into the various frequency components. Once they're sifted into the frequency components, the one that you're looking for is extracted using a filter, which is also defined in software. The carrier is removed via the software, the demodulation process, and the resulting signal is converted from the digital signal to analog so that it can be heard from the speaker or headphones. A very basic look at the software-defined receiver. Now let's look at the transmitter. Again, we have the microphone. The audio signals from the voice are converted to digital, fed to the digital processor. All of the work is done here. The resulting signal ready to be transmitted is converted from digital to analog, fed into our power amplifier, and then off to our transmitting antenna. So speech converted from analog to digital. The modulated signal is generated using software, here in our digital processor. And the resulting signal converted from digital to analog, D to A, amplified with the power amplifier and fed to the antenna. That's about it for this module. A quick summary. You'll need to remember those block diagrams for transmitters and receivers, and of course software-defined radios. Don't just learn the numbers, learn the meanings of those boxes. Then we have the modulation types. We have AM, amplitude modulation, and frequency modulation. It's quite common, they'll show you the 2 diagrams and ask you which is which. Then there's the basics of single sideband, lower sideband below 10 MHz, and upper sideband above 10 MHz. And I'll look at software-defined radios. That's where all of the processing is done in software, not in hardware. And reminder of transmitter usage, don't transmit out of band, and be careful of those audio levels, make sure they're not too loud, otherwise you will overmodulate or overdeviate. And that's about it for our transmitters and receivers module. Thanks for watching this latest module of our Foundation online course. We hope you found it useful. If you're looking for some more help with your studies, we do recommend the Foundation Study Guide, available from Amazon in Kindle or paperback format. Thanks for watching again, and best of luck with your studies. As a reminder, this video is part of the free Foundation online course. If you're studying for Foundation, sign up and get access to all of the course material, including slides, lessons, handouts, videos, quizzes, and our mocks. You can sign up at www.hamtrain.co.uk.